All right, so today is our first class on steady state sinusoidal circuit analysis. And so we are going to start by looking at signals in the time domain. In a little bit, I like to call forced response due to sinusoidal analysis. Excuse me, sinusoidal inputs. All right. So can anybody recall what the concept of a forced response has to do with? All right. So let's say that I have the following circuit. I apply some DC voltage to a resistor R in series with some inductor L. And I'm going to define my response to this as my DC current I. Based on your level of circuit analysis knowledge, what should my forced response here be? Not remotely a trick question. What is I in this circuit? VDC over R, absolutely right. So for a DC forcing function, which is just our DC source in this case, we know that our response I is also a DC signal. And from this, using Ohm's law, we could see that the voltage drop over resistor R has a DC value of exactly VDC, and voltage drop over inductor L has a DC value of exactly 0. So if we use a DC excitation source, all of our signals are DC signals as well. So what if we have the following system? We have a time domain voltage being applied. And we should observe that after any transient conditions have died out, so we're only dealing with a forced response, our response should be of the exact same form. So if V of t is equal to Vm cosine omega t plus some phase angle theta v, and I'm going to argue just for math's sake that we're going to treat this as 0 degrees for now. Our forced response should be of the form Im cosine omega t plus some phase angle theta I. So we're saying that if we apply a sinusoidally varying input with some particular magnitude and some particular phase angle, we should expect to a linear system, we should expect to see that our response, in this case our current, is a sinusoidally varying signal as well with a particular magnitude and a particular phase angle. It wouldn't matter if I changed my response to be the voltage drop over the resistor or the voltage drop over the inductor. They would all be of this generic form. So if we did a little bit of math here, we can see that V of t is equal to VR of t plus VL of t, which is in turn simply R times IL plus L times D IL. With our guess value of I of t, we are going to have the sum of two sinusoidally varying signals, right? Which would allow us in some shape or form to calculate what IL is. The problem that we are facing right now is that if we work this problem entirely in the time domain, it's going to be very, very tedious. We are going to do just that, and it will take the majority of our lecture, okay? So using our guess value that IL of t here must be of the form I am cosine omega t plus some phase angle theta I, and I'm going to use a trig identity here that says cosine of alpha plus beta is equal to cosine alpha, sorry, go away, cosine alpha, cosine beta, minus sine alpha, sine beta. I can rewrite this guy as I am cosine theta I cosine omega t minus I am sine theta I sine omega t, which I will call A1 cosine omega t plus A2 sine omega t. So I've effectively just deconstructed this guy from a single sinusoid to the sum of sinusoids. And I want to be clear here. A1 is I am cosine theta I, and A2 is negative I am sine theta I, because we're going to have to use those results to circle back around to our answer that's of the correct form. All right. So if I substitute this representation of my guess value into my first order differential equation that I have here, what I will get is that Vm cosine omega t, again, we're choosing here to set theta v is equal to 0 purely to make the math easier, will be equal to R times A1 cosine omega t plus A2 sine omega t plus L d by dt of that same thing, A1 cosine omega t plus A2 sine omega t. And if we perform the indicated derivative, that gives us Vm cosine omega t is equal to R A1 cosine omega t plus R A2 sine omega t minus L A1 omega sine omega t plus L A2 omega cosine omega t. And I'm just going to group like terms real quick. So for my cosine term, I have R A1 plus omega L A2. And for my sine term, I have R A2 minus, sorry, hold on, let's see. My cosine, yeah, minus omega L A1 sine omega t. And what I'm about to do is use the, effectively, I think it's called the Law of Undetermined Coefficients, that we can make some equivalencies here, all right? So for example, on the left-hand side of my equal sign, I have the quantity Vm times cosine omega t. And on the right-hand side, I have a quantity R times A1 plus omega L times A2 cosine omega t. So that means that Vm has to be exactly equal to R times A1 plus omega L times A2, okay? So I can say R A1 plus omega L A2 is equal to Vm. And similarly, I can say that R A2 minus omega, sorry, shouldn't be lowercase l. We'll be dealing with that later. A1 is equal to 0, and I have a simple system of equations, two unknowns, which yields the following results. A1 is equal to R times Vm over R squared plus omega squared L squared, and A2 is equal to omega L Vm divided by that same magnitude. So we'll have R squared plus omega squared L squared. And from this, we could say that IL of t is then R Vm over R squared plus omega squared L squared cosine omega t plus omega L Vm divided by R squared plus omega squared L squared sine omega t. So we have a functional form of the current circulating through our simple three-element system, but expressed in terms of our known values. We know what our excitation frequency is. We know what our excitation magnitude is. We know what the value of R is. We know what the value of L is. Our problem here is that at present, our expression for I of t is not in the same form. And because we are exciting it by a sinusoidal function with some phase angle, we should expect our response to be of that exact same form. So we have done a significant amount of work to be able to tell what I is in terms of our circuit parameters. And we're technically only halfway there to get it into the form of an answer that we would like to see. So I can use a couple of trig identities. So since we know that, well, let's do this here. We know that A1 is equal to RVM over R squared plus omega squared L squared. And this is also equal to Im cosine theta I. And we know that A2 is equal to omega L over R squared plus omega squared L squared. And this is equal to negative Im times sine of theta I. We can use the following two trig identities to figure out what the magnitude of our current is and the phase angle of our current is to give us our answer in the form that we are expecting. So I can say that Im times the cosine of theta I squared plus Im times the sine of theta I quantity squared is equal to Im squared times cosine squared theta I plus sine squared theta I, which is exactly equal to Im squared, since cosine squared plus sine squared is equal to 1 from your high school trig class. So from that, we have Im squared is equal to R squared Vm squared divided by R squared plus omega squared L squared quantity squared plus omega squared L squared Vm squared divided by R squared plus omega squared L squared quantity squared. So that's just my Im cosine theta I squared plus my Im sine theta I quantity squared, which I know has to be equal to Im squared. So I can put things together, and this is going to look like Vm squared times R squared plus omega squared L squared divided by R squared plus omega squared L squared quantity squared. And from this, I have Im is equal to Vm divided by the square root of R squared plus omega squared L squared. So I can now, I have an expression for the magnitude of my current in terms of all of my different circuit parameters. So what I'm left with now is figuring out how to get this guy theta I. So for theta I know that the tangent of theta I, by definition, will be the sine of theta I divided by the cosine of theta I, right? Basic trig rule. Does it harm anything if I have Im times sine theta I over Im times cosine theta I? No, right? Well, this is simply negative A2 divided by A1, which means theta I is equal to the arctangent of negative A2. So that would be negative omega L divided by R squared, plus omega squared L squared divided by A1, which is R multiplied by VM. Sorry, there should be a VM there as well, right? Yeah, I messed this up here. That should have been a VM. Divided by that same denominator, R squared plus omega squared L squared. These denominators cancel each other out. The VMs cancel each other out. And so we get theta I is equal to the inverse tangent of negative omega L over R, which is the same as negative inverse tangent of omega L over R. And putting all of this together, we get IL as a function of time is VM divided by the square root of R squared plus omega squared L squared times the cosine of omega t minus the inverse tangent of omega L over R. So I now have a means by which to express my currents, IL of t, in the exact same form that I was able to express my excitation function, which was my voltage V of t. So, how awful was this? Absolutely terrible, right? If we had to do this for every single problem, the field of electrical engineering would not exist. We would have just said, screw it, we're okay with just using fire for light, and you know, who needs phones and all that kind of stuff, all right? Notice we spent just a crap ton of math, really, analyzing a circuit that contained two elements other than our source, right? If we put a resistor, another resistor in parallel with that inductor, that would increase the level of complexity of the math by 5-fold easily, okay? What we have done here, all of this math is only valid for this very specific case where we want to know the current flowing through a resistor in series with an inductor. So we need to figure out a better way of doing things, all right? So what some people did, people much smarter than me for sure, figured out is that this sinusoidal number, or excuse me, this sinusoidal time domain expression, Vm cosine omega t plus theta v, is the real part of a complex number, all right? So I can say that this is the real part of the complex number Vm e to the j omega t plus theta v. And similarly, I can say that this guy over here, my current, is the real part of the complex number e to the j omega t plus some phase angle theta I. Now you may be saying to yourself, all right, so now you can express things in terms of complex numbers. How on earth does that help? Reasonable question. So let's talk about things just real quick. Let's say that I have a linear black box circuit. And I apply to it some signal. I'm going to call it V1 of t. And I measure some current, its response, as I1 of t. Well, we have proven that if V1 of t is of the form Vm cosine omega t plus theta v, then I1 of t will be of the form cosine omega t plus some phase angle theta I. That's all that terrifying math we just did, is proving this equivalence, all right? Let's say I take the exact same linear black box circuit. And I apply a new signal, V2 of t. And I measure a response, I2 of t. Let's say that V2 of t is of the form Vm sine omega t plus theta v. What is our expectation for our response? So when we put in a cosine, so when we put in as our input something cosine omega t plus theta v, we got out something cosine omega t plus theta I, right? So I would argue that mathematically, if we put in a sine instead of a cosine, we should get out a sine as well, right? Another way that we could think about this sine omega t plus theta I is that the sine function and the cosine function are the same thing. There's just a slight time shift, right? All right, so how many of you remember anything about the scaling property of linearity? So the scaling property of linearity says that if I scale my input by some fixed non-time varying amount, I should expect to be able to scale my output by the exact same thing. So just as a very, very quick proof, for a simple linear circuit, if I have 2 volts and I have a 4 ohm resistor, my input is 2 volts, my response is this current I should have a current of 1/2 amp, right? So if I double my input voltage, does my output response also double? Yes, okay. For any linear circuit, that will be true. So if I put in 4 volts, I should expect to see 1 amp. If I scale my input by a factor of -1 volt, I should scale my output by a factor of, if I scale it by a factor of -1/2, I'll scale my output by a factor of -1/2 as well. So with that scaling property in mind, if I were to scale my input by a factor of the imaginary operator j, I can then scale my output by that exact same factor J as well, because J, while it is imaginary, is not a time varying quantity, right? It is by definition the square root of -1, or here in electrical engineering represents a phase shift of exactly 90 degrees, which we'll get into in a little bit. Now, let's take this one step further. My same linear black box network now I'm applying V1 plus V2. My response, due to the additivity property, should be I1 plus I2, right? So this is that whole superposition, well, it's called superposition in your circuits 1, but superposition actually involves the scaling property as well. So this is really just the additivity. So what this means is if I have a circuit with two sources, a linear circuit with two sources, I can analyze the circuit with only one source on, get a response, analyze the circuit again with only the second source on, get a response, and the total response is simply the sum of the responses with each one on, right? You guys have done several homework problems with that way back in circuits 1, and we are going to use superposition again over and over and over in this class. So what this means is that the total input, V of t in this case, is of the form Vm cosine omega t plus theta v plus j Vm sine omega t plus theta v. And my total current is Im cosine omega 2 plus theta I plus j Im sine omega t plus theta I. Well, there's a trig identity called Euler's identity, which I'll write down over here, that says that e to the j x is equal to cosine of x plus j sine of x. So using Euler's identity, V of t here is Vm e to the j omega t plus theta v. And we can also express our current I as a complex number as well, but I'm not going to do that. The reason why I want to leave it in this form is because I want us to notice something very particular about this linear black box circuit that is representative of any circuit we could create containing resistors, capacitors, and inductors. The real part of the response, meaning the part that doesn't have a J in front of it, is due entirely to the real part of the excitation signal. And the imaginary part of the response is due only to the imaginary part of the excitation signal. So I can apply a complex forcing function at my input to represent this time domain signal, and I can get an answer that is absolutely correct 100% of the time by simply taking my output complex number and only looking at the real part. So let's analyze that exact same circuit. We have V of t like so. Here's my resistor R. Here's my resistor L. Here is my current I of t. Here's VR of t. Here's VL of t. I'm going to say that my voltage V of t should be of the form Vm e to the j omega t plus theta v, where I'm going to set that guy equal to 0 degrees again. And my expectation is that my current is going to be of the form Im e to the j omega t plus theta I. And I would argue that I should find that the magnitude of my complex response and the phase angle of my complex response will exactly match the answers that we got doing all of that calculus and trig identities and all that kind of jibber jabber, okay? So, if you recall, I had a differential equation that said that V of t was R times I of t plus L times di by dt. If I put in my new guess value, my new response type, I'll have Vm e to the j omega t is equal to R times Im e to the j omega t plus theta I plus L d by dt of that same quantity Im e to the j omega t plus theta I. What I'm going to do now is I'm going to split all of those exponential functions, okay? And so what I mean by that is I am saying that e to the j omega t plus theta I is the same as e to the j omega t multiplied by e to the j theta I. Everybody okay with that? When you multiply two exponential functions together, you simply add the arguments, all right? So if I do that, I can observe that there is a common factor of e to the j omega t that's showing up in every single term, both on the left-hand side and the right-hand side. And so I'm going to divide through by that factor of e to the j omega t, which leaves me with Vm is equal to R times Im e to the j theta I plus, when I take the derivative with respect to time, I'm going to have a j omega that gets pulled down. So I get j omega L times Im e to the j theta I. Grouping like terms, then I have R plus j omega L is equal to Im e to the j theta I. And finally, I get Vm divided by R plus j omega L is equal to Im e to the j theta I. So I've gotten to the halfway point again in this problem, using significantly less math and exactly 0 trig identities. So I feel like we've done a little bit of work here. So at this point, we need to recognize something that maybe isn't intuitively obvious, okay? The number on the right-hand side, Im e to the j theta I, is simply a complex number in polar form, right? It has some magnitude, Im, and it has some phase angle, theta I. The number on the left-hand side, Vm divided by R plus j omega L, is also a complex number. It's just in rectangular form. And we know how to convert rectangular form complex numbers into polar form complex numbers and vice versa. So now we really just need to, all we really need to do is figure out how to convert that rectangular form number into a polar form number so that we can look at its magnitude and look at its phase angle. And that's fairly straightforward, right? So if I have Vm divided by R plus J omega L. Actually, let me make a quick note up here. All right. So we know that for a complex number A, which is equal to A plus JB, or alternatively in polar form, we'd have E to the J theta A. We know that A is equal to cosine theta A, and B is equal to sine theta A. Here we know that our magnitude, which in this case would be 1, is the square root of A squared. Actually, let me do it this way. So I'm no longer assuming that the answer is 1, is effectively all that's going on here. That magnitude A without a bar over it, sorry, just a second, is giving me that error, so I gotta save and restart. All right. Is equal to the square root of A squared plus B squared, and our phase angle theta A is just the tangent of B over A. Those are our complex number relationships to move back and forth between rectangular form and polar form. All right, so once we can express our left-hand complex number as in this form where it's simply some number plus J, some other number, getting the magnitude and getting the phase angle is trivial, right? So let me ask you guys a question. It's okay if you don't know the answer to it right off the bat, but how can I make that complex number V over R plus J omega L, how can I get it into this form? Where instead of having a complex number in the denominator, it looks like I have a complex number in the numerator. Absolutely correct. So the complex conjugate of the denominator, right? So I'm going to multiply this by, what's the complex conjugate of my denominator? Somebody tell me what that is. R minus J omega L. Complex conjugate, we just flip the sign on J. So we'll have R minus J omega L times R minus J omega L. So that is going to look like Vm times R divided by R squared plus omega squared L squared minus J omega L Vm over R squared plus omega squared L squared. All right. So Im, in turn, has to be the square root of VMR divided by R squared plus omega squared L squared. Sorry. Quantity squared plus, here I'll have negative Vm omega L divided by R squared plus omega squared L squared, quantity squared. So what's going to happen is I'm going to get the square root of Vm squared times r squared plus omega squared L squared divided by r squared plus omega squared L squared quantity squared, which means my magnitude Im is exactly equal to Vm divided by the square root of r squared plus omega squared L squared. And my angle, theta I, is the arctangent of B. So that would be negative omega L Vm over r squared plus, sorry, no J, omega squared L squared divided by A, which is r times Vm divided by r squared plus omega squared L squared. The denominators cancel, the Vm's cancel, and we get arctangent of negative omega L over r, which is the same as negative arctangent omega L over r. So we have the exact same magnitude and the exact same phase angle. And we got there more quickly, but not super quickly, right? So it was less calculus for sure, all that kind of stuff. We just had to take a simple derivative where when we take the derivative of these complex numbers, it's just multiplying by a factor of omega L, but we didn't have to switch back and forth and do all those trig identities. So this was definitely easier, but not as easy as it could be, all right? So we can make things easier by working in what's called the phasor domain, all right? And so the phasor domain is just a shorthand notation that electrical engineers came up with, all right? So if we have, let's start over here. Let's call this guy the time domain. Our voltages, V of t, will be of the form Vm cosine omega t plus theta v, and our currents, I of t, will be of the form Im cosine omega t plus theta I. We just analyzed the circuit in what I call the mixed domain. In that mixed domain, we represent our time domain signal by a complex number. So Vm e to the j omega t plus theta v, and I of t is equal to Im e to the j omega t plus theta I. The phasor or frequency domain is simply our mixed domain representation, but we suppress our frequency term, okay? So let me talk about that real quick. We observed in the previous example problem at around this step right here that everything was being excited at the exact same frequency. Everything had a common factor of e to the j omega t. So we are going to begin by completely suppressing that. So we're saying that is redundant information. We are no longer going to carry it along with us, all right? So our phasor domain representation, we're going to have a phasor voltage V, and it is going to be Vm with an angle of theta V. And similarly, we're going to have a phasor domain representation of current that just carries along the information of magnitude So any voltage, we can express a phasor representation by looking at the magnitude and the phase angle. Same thing for any current. All we care about now is magnitude and phase angle. I want to be very, very clear here. We are starting under some very specific constraints, okay? Constraint number 1, all signals are expressed as cosine functions, okay? So if we have anything that's expressed as a sine function, we need to convert it to a cosine function. How do we do that? Anybody remember from Circuits 1 or your basic trick? Do we add or subtract 90 degrees? Subtract, all right? So sine omega t is equal to cosine omega t minus 90 degrees. Our second condition is that all signals are expressed with a positive magnitude. All right, so meaning if we had negative cosine omega t, that is the same as positive cosine omega t plus or minus 180 degrees. Under those two conditions, we can now develop relationships for all of our circuit elements of interest and vastly simplify the math needed in order to analyze a circuit. Let's see what I got here. Did all that jibber jabber. That. All right. Okay, I'm where I am. Good deal. Okay. So we got about 20 minutes left, so let's take care of some business here. So let's say we have a resistor. Has some resistance R. We have a time domain current I of t flowing into it. And a time domain voltage V of t across it. All right. What is our current voltage relationship for a resistor? V is equal to IR, just good old Ohm's law, right? So we know that V of t is equal to R times I of t. So if we applied our mixed signal relationship, this would give us Vm e to the j omega t plus theta v is equal to R times Im e to the j omega t plus theta I, right? We're simply replacing V of t with our complex representation of V of t. We're replacing I of t with our complex representation of I of t. We can see that there is a common factor of e to the j omega t on both sides, which gives us Vm e to the j theta v is equal to R times Im e to the j theta I, or V phasor is equal to R times I phasor, where I phasor and V phasor are simply Vm angle theta v, which is the exact same thing as Vm e to the j theta v. And this is the exact same thing as Im e to the j theta I. So the exponential flipping back and forth in our heads between the exponential form and the polar form because they represent the exact same thing, just magnitude and phase angle. A couple of things that we can notice about a resistor here real quick. What is the relationship between the phase angles here? They have to be exactly the same, right? So if we look on the left-hand side, we have a complex number with a magnitude of Vm and a phase angle of theta v. And on the right-hand side, we have a complex number with a magnitude of r times Im and a phase angle of theta I. The magnitudes of both sides have to be equal, and the phase angles of both sides have to be equal, which means that theta v is exactly equal to theta I for a resistor. And the magnitude of V is equal to R times the magnitude of I. Or alternatively, Vm is equal to R times I. All right, so the resistor is pretty trivial. Now let's look at an inductor. Have that current I of t flowing in, voltage drop V of t across it like so, and we know, that V of t in this case is L di by dt, right? So doing the same thing, we have Vm e to the j omega t plus theta v is equal to j omega L times Im e to the j omega t plus theta I, which means Vm e to the j theta v is equal to j omega L Im e to the j theta I, or V phasor is equal to j omega L times I phasor. Now we know that Vm is going to be equal to omega L Im, all right? And we know that theta V is going to be equal to theta I plus 90 degrees. Where this is coming from is the fact that there's an extra factor of J here out front. If we looked at a complex plane and we represented the number 1 on the real axis, that would be 1 plus J0 as a rectangular number and 1 angle 0 degrees as a polar form complex number, right? Well, if we look at J on the imaginary axis, that is 0 plus J1, which is 1 angle positive 90 degrees. So I have 1 e to the j 90 degrees times 1 e to the j theta I. I add the arguments together, and that is why theta v has to be equal to theta I plus 90 degrees. Okay. Lastly, we have a capacitor. I guess I'll do it on a different sheet of paper here. current flowing in this way, voltage drop occurring with this polarity, and our current voltage relationship is I is equal to C dV by dt, which gives us Im e to the j omega t plus theta I is equal to j omega c Vm e to the j omega t plus theta v. Suppressing my frequency terms gives me Im e to the j theta I is equal to j omega c Vm e to the j theta v. And so I can see that I phasor is equal to j omega c V phasor, or alternatively, V is equal to 1 over j omega c times I phasor, giving us the relationships Vm is equal to Im divided by omega c, and theta v is equal to theta I minus 90 degrees. So these are our phasor-based relationships for voltage and current across any circuit element: resistor, capacitor, and inductor. Okay? So we do have one other thing that we're going to talk about. Is we're going to kick off probably the next lecture with it. But let's see if we can use these relationships to figure out what's going on in that circuit that we've been analyzing over and over again and see what falls out, right? So we have this guy. EBR of T. You know what, I take that back. Let's talk about impedance, and then we'll get into circuit analysis on the next time. All right, so the next big step in phasor domain circuit analysis, we have all of our current voltage relationships and all that kind of stuff. Sorry about making an array set. All right, so the next thing that we're going to do is we're going to define what's called impedance, okay? So in a DC system, it can be shown that for a generic DC network where we apply some voltage V, there is some current I flowing into the terminals, and the resistance of said network is simply the ratio of V divided by I, right? Well, impedance is the concept of resistance, but in the frequency domain. So if I have an AC network, and so what I mean by that is a network that's being excited sinusoidally. If I apply some phasor voltage V and observe some phasor current I flowing into the network, then the impedance of the network, Z, is equal to the phasor voltage V divided by the phasor current, I. So impedance is playing the role of resistance in our AC circuits, right? So a couple of things that I want to point out about impedance. This is going to be Vm angle theta V, Im angle theta I. So we would have Vm over Im with an angle of theta V minus theta I. This gives us our magnitude of our impedance and our phase angle of our impedance. So we can express our phase angle, or excuse me, our impedance as a complex number having a particular magnitude and a particular phase angle. Additionally, we can express our impedance in terms of a rectangular system. R as a function of frequency plus Jx as a function of frequency, where R is the resistance, and it is the real portion, and X is the reactance, and it is the imaginary portion. And we can convert back and forth between the rectangular form and the polar form as follows. The magnitude of Z is equal to the square root of R squared plus X squared. Our phase angle, theta Z, is equal to the arctangent of X divided by R. The real part, R, is simply the magnitude of Z cosine theta Z, and X is then simply magnitude sine theta Z. So, as a quick aside here, which is really the crux of what I wanted to talk about, I think this will be enough for today because we're running out of time anyway. If I wanted to know what the impedance of a resistor was, I can simply scroll up here and look at the equations that I developed, right? This describes perfectly the phasor relationships for a resistor. Impedance, by definition, is phasor V divided by phasor I. So what do I get? R. So the impedance of a resistor is the resistor value itself. Nothing weird there. So I can express this as R, and just for the sake of argument, I'm going to put it as R plus J0, meaning it has a purely real resistance and no reactance whatsoever. And in polar form, I'm going to say that it is R angle 0 degrees. Just because sometimes it might be helpful to do this, okay? So we have R plus J0 and then R angle 0 degrees. What about an inductor? So let's scroll up here and look at what's going on with our inductors. We can see that V divided by I is equal to J omega L. So I'm going to call that 0 plus J omega L. And in polar form then, that's going to be omega L angle positive 90 degrees. For a capacitor, I'm going to have 0 plus 1 over J omega C is equal to 1 over omega c with an angle of negative 90 degrees. Now there's one thing that I want to point out here real quick. Some of you, depending on who you had as your professor in Circuits 1 and all that kind of jazz, might have seen ZC expressed as negative J divided by omega C, okay? So if I have 1 over J and I multiply it by J over J, that gives me J over J squared, which is negative J. So just to be clear here, we could also express this guy as 0 minus J divided by omega C, which is still going to give us 1 over omega C with an angle of negative 90 degrees. All right, I think that is enough out of me for today. We went almost full time. When we get back on Friday, we're going to talk very briefly about the concept of admittance, and then we're going to get into circuit analysis. So actually, before I let you guys out, I want to look at the schedule in this class real quick. We can just talk about a couple of them here. All right, so on Friday, it says that we were supposed to talk about impedance, which we have already covered. And then we were going to talk about admittance and phasor circuit analysis. And then on Monday, we had more phasor circuit analysis and then multi-frequency circuit analysis. So this guy right here, this phasor circuit analysis, we're going to be able to talk about 40 to 45 minutes on. And then multi-frequency circuit analysis might only take 20 minutes or so tops. So I guess my question to you guys is, how much of a review do you feel you need on frequency domain or phasor circuit analysis? It is what you covered in the third part of Circuits 1. So like how much detail or how much do I need to beat this dead horse? Okay, so the general consensus is that was the part where people tended to slack off. Okay, that's the reason why we're reviewing here. Okay, I have no problem whatsoever effectively dedicating 2 full days to that. I just wanted to make sure you guys weren't going to be bored to tears with it. You might still be bored to tears, but at least you admit you need it, so that's okay. All right, well then I'll see you guys on Friday, and we'll jump into frequency domain circuit analysis. All right, have a good rest of your day.